Yeah.
Small suggestion that
Yeah.
when you're writing,
Yeah.
don't write too long like this. In the camera, it will come very small. We have to capture not this much.
Okay.
So you, if possible, just make it like this one column. Then you write in that.
Okay. Yeah. Only in the beginning I write like this. Yeah.
No.
After that. Yeah. Okay. Got it. Got
Because
it.
some people putting messages that just zoom out. Then
Okay.
if I too much,
You can't read.
Yeah, this will come very small.
Okay. All right. I'll keep in mind. Is there a sign-up sheet for attendance going around already? Not yet? Okay, then the TAs should come around at some point and pass around a sign-up sheet. If by the end of the class it hasn't come to you, please remind me. Yeah. Okay. Okay, it's 11, so we can start. All right, so welcome to the last class for this module. We've been working up to doing population dynamics first with one species, then with two species, and today we're going to think about how we can think about population dynamics of many species. Okay, in particular, when you talk about many species, there are many different ways to think about it. There's one sort of physics tradition which often likes to say that there are only three problems that we can solve in physics. There's a one-body problem, there's a two-body problem, there's the infinite body problem. And so in some sense, we're going to try doing the infinite body problem today. Turns out that everything in the middle is very difficult. You might have heard of the three-body problem and so on and so forth. So we're going to try and implement some ideas from that today. Again, in a longer course, we would really take this StatMech approach to heart and do some more involved things. But today's class should give you a flavor of what it is that we are trying to do. And we have to choose a model in which to think about doing these dynamics. So we're going to continue building on this Lotka-Volterra competition framework that we've been building on. We're going to study a generalized version of that today. By generalized, I mean one that doesn't have just two species, but many species. And this is perhaps the simplest form of these kinds of dynamics that we can write down. There are also these resource explicit dynamics that many of you have been asking me about, which we are not going to talk about in this module. And again, towards the at the end of this class, I can give you some more references if you're interested. And there are really two things we're going to focus on once we set up the model. One is, well, first of all, we're going to care about how we get all these alphas or interaction terms from, right? How would we ever talk about them? And in particular, there are two approaches. One is to go and measure them experimentally. But we'll see as the number of species gets very large, that becomes very difficult. And so there's an approach that comes from physics that was pioneered in ecology way back in the 70s, so more than 50 years ago by Robert May, which is an approach to think about a matrix of interactions as a random matrix. And that gives us the ability to at least talk about statistical features of many species systems. And so the two things about these statistical features that we're going to care about today is one is this concept of feasibility, which is what's the chance that you put a set of species together and they can coexist with each other. And we'll often find that they sometimes cannot coexist with each other because a fixed point means one of the species abundances has to become negative, right? The other thing that we care about, and this is really, I think, going to be the bulk of this class, is this extremely surprising result which comes from Robert May, again, about 50 or so years ago, which is that by thinking of these matrices of interactions as random matrices, you get this extremely surprising result, which goes contrary to our observation or intuition, which is that the more species that you have in a system, the less stable it should become. And generically, what we're going to see by the end of today's class is that actually you shouldn't be able to have arbitrarily large species diversity, because all those sets of species should become can only coexist at an unstable fixed point, right? And so finally, I'm going to maybe end in the last 5 minutes by telling you how in today's research, 50 years from May, we kind of are attempting to resolve this conundrum. Yeah, but it's only been very recently that people have started to look at this. Okay, is it clear where we're going to, today? Okay, great. So let's talk about many species dynamics, and in particular, let's talk about this generalized Lotka-Volterra model. So in two species dynamics, we wrote down a model of competition where each species was growing logistically on its own, right? And the presence of the other species did what? Yeah, but what did it do to the dynamics? What did the presence of the other species do to the dynamics of any species that we cared about? It affected the per capita growth rate, right? And did it affect it quadratically, polynomially, linearly, right? Does that mean that the Lotka-Volterra model is a linear model? No, right? It's a non-linear. Why is that?
Per capita thing is modulatively it is multiplied by the...
Yeah, correct. Yeah, so we have, so in general, when you have S species, for each species, you can write down one equation for the dynamics of its population abundance. And the most general version of this will look something like this. Yeah, this is just the generalization of the model that we wrote in the last class, right? I'm still writing it with all the carrying capacities so that you can see it, but we're very quickly going to get rid of this, right? So now the only thing that the presence of many species has done is what? Each of the other species has a linear effect on the per capita growth rate on each of the other species. Right? So this in your old version, if there's just one more species, that's just going to be beta 1, 2, and 2. If there's a third species, there's going to be a sum of beta 1, 2, and 2, and beta 1, 3, and 3. Right? And so on and so forth. You can kind of work this way around. Right? This is not usually the version of the model that we'll be dealing with. We'll be dealing with the one with the change of variables, where we deal with things which are normal, where all the species abundances are normalized to their carrying capacities. And there's many different versions of writing this, but one version that you can write down will look something like this. Right, so now the S equations, one for each species. Right? Is it clear why I wrote J not equal to I in this sum? Where's the J equals I? That's outside, right? So I've implicitly assumed something about the species interaction with itself. Right? And we've assumed that there's an AII secretly. That's one. Right? And we can even think about a simpler version of this model where all the RIs are set to 1. So that makes life even easier for us. Right? That's just a multiplier that shouldn't change any of the qualitative behavior of the model. Just the quantitative behavior of the model. And so in this case, it turns out that there's really only one thing that we need to care about, which is this entire set of A's. Right? All the interactions of species with each other. And what kind of object will that be? That's a matrix, right? and it helps to explicitly try to draw out this matrix at least once, right? So this is Aij, right? And if I wanted to really make this matrix, I have to think about the diagonal entries of this matrix, right? What should I think about the diagonal entries of this matrix as? Let me just try and incorporate this whole thing, right? So this would give me all diagonal entries as 1, right? And then there are all these off diagonal entries. It also helps to think about what the rows and the columns are, right? So what does Aij really say? It is the interaction between two species, but are we assuming something about how I interacts with J and J interacts with I? Sorry? Well, here there are no resources, right? This is there are no resources in this model, so we never can talk about resources, right? Yeah, that's right. So Aij, the convention that we use here is J interacting with I, right? And I drew this blunt arrow because it's usually some sort of competition or some sort of inhibition, and in that inhibition, usually we draw inhibitions with these blunt arrows and provision of facilitation with a pointed arrow, right? What about AJI? AJI is how species I suppresses J, right? Have we made some assumption here about whether they should be the same or not? Ready, 3, 2, 1. Yeah, we haven't, right? They can be whatever they want. And so in principle, the Aijth term, yeah, will it be, okay, so there'll be one term here and one term here, right? They'll be mirror opposite each other. So is this one okay, I have to tell you which is larger and which is smaller, right? So let's say, yeah, where is A27? Could it be this one or that one? Yeah. Is it the one below or the one above? Ready? 3, 2, 1. Yeah, it's here, right? And so A72 is over here, right? So in some sense, there is a from part of an interaction, right? Where the inhibition is coming from, and then there's a to part of the interaction, which is where the inhibition is going to, right? It's from J to I. That's Aij, right? So in some sense, on these rows and columns, I can also write a from and a to, right? So should I write the from in the rows or in the columns? Ready? 3, 2, 1. Right, in the columns, right? And this is 2, right? And all of these indices are what? How many entries are in this matrix? There's S by S, right? And so there are S rows and S columns. And so this is species 1, species 2, species 3, all the way down to species S. This is also 1, 2, all the way to species S. Right? So it helps to kind of have these labels on here at least when we are starting to help remind us what this matrix is really saying. Right? And so what these dynamics are really telling us is that the only thing you need to tell me, at least for now, is what this matrix is, and then I can tell you something about what kinds of configurations this ecosystem can be in. Right? So yeah, how many entries do I need to fill in this matrix that I don't know? I know a bunch of ones, right? How many entries do I need to fill in? S square minus S, right? How do I get them? Okay, we can get them through experiments. What kind of experiments should we do? Do you mind being a little bit louder?
How each species inhabits or interacts with each other species in the system.
Yeah, that's what the matrix means, right? How would I get those? How would I get these values?
By measuring how their population is changing over time for each of them.
For each of them alone?
We'll take each species and put them together.
Right. Yeah, so you take each pair of species and then you grow them together, and then what do you get by doing that?
How their population is changing over time.
Yeah, so you get their dynamics, but we want Aij and Aji, right? How do we get those?
Fit them to the two species log.
Yeah, you fit them to the two species Lotka-Volterra model. And then, yeah, so if you have the dynamics, you can fit it to this model, and then you're done. So every time you do one experiment, how many numbers do you get? 2, right? So how many experiments do you need to do to fill in this entire matrix if there are S species? 2 to the power S squared minus S. Why 2 to the power S squared minus S? Every time you're getting 2. And how many do you need? You need S square minus S, right? So how many experiments? So every experiment you do, you get 2 numbers. You need S square minus S numbers. So how, yeah?
2 into S square minus, not 2 to
Do you need 2 into S square minus S or S square minus S by 2, right? You need S square S into S minus 1, right? Every time you do an experiment, you get 2. If every time you did an experiment, you got 1, how many experiments would you have to do? These many. If every time you did an experiment, you get S square minus S, how many would you need to do? 1, right? So then, this is how many experiments that you need. Okay. So you can see that the number of experiments that you need to do goes quadratically with the number of species, right? Just draw a plot. Number of species, number of experiments. Go something like that. Do people have a sense of how many species really are out there typically in some species ecosystem that we might care about? Let's take a poll. This is always interesting. So, I mean, we can take an example. So, let's say you go and dig a part of the soil. You take like 1 milligram of it. Maybe let's say take 1 gram of it. How many species do you find? Let's take a poll. How many? These will typically be microbial species. But sometimes you might find bugs also, right? 1 soil. Is it A? No, 10, 1, 10, 100, 100,000, greater than 1,000. Okay. Should we have a poll? So there's 1, 10, 100,000, and or maybe more than 1,000. Ready? 3, 2, 1. If you don't know, you can feel free to guess something. No one's adventurous enough to say 1. No one's adventurous enough to say greater than 1,000. Okay, some folks are. Okay, yeah. So okay. So first of all, the question of how many species there are is a very contentious topic. But I would say that it would be hard to argue that this number is anything less than 1,000 by most metrics. Even 1,000, I would say, is acceptable. But yeah, it's in the thousands typically. Okay, so how many experiments do we need to do if I want to describe a soil ecosystem? Then this is just one gram. Yeah. So is that happening? You think you can convince yourselves, or Anyone around you to do that many experiments? So are we? So then should we stop doing ecology? It's a lost cause. So there are other ways. So actually, curiously enough, does anyone know the story of Wigner and the uranium nucleus? Okay, so I mean, obviously people used to care about still care about uranium a lot for various reasons. Around the Second World War, they cared much more than they care right now. And a lot of people were trying to figure out various things about uranium, including how the nucleus works, because they wanted to do certain things with it. And so Wigner was one of these physicists who cared about the uranium nucleus. Does anyone know what's inside a uranium nucleus? In any nucleus, typically there are protons and neutrons, right? So, but you know how many? Yeah, 235 things, right? Some of them are protons. So there's about 92 protons and the rest of them are neutrons, right? And usually one way that people study nuclei is by studying the Schrodinger equation. And for those of you who are from a physics background, you would have solved the Schrodinger equation for the hydrogen atom. Yeah, it's not happening for the uranium atom, right? So Wigner and other people still care about the uranium nucleus. So what did they do? They gave up nuclear physics. They perturbed what? The uranium nucleus. Nuclear potential. Can you say more?
They have tried to describe a potential value for the nucleus to describe the radiation.
Well, okay, I would say they wanted to understand, okay, good. The question is, what do you want to understand about the uranium nucleus, right? So one of the experiments that they were doing at that time was that they were bombarding the uranium nucleus with things, right? And you can use this bombarding thing to figure out what the energy resonances are. You bombard it with things with different energy, you can get the energy resonances of the uranium nucleus, right? And you can go and make this spectrum where this is the energy, and you find these kinds of peaks, right? And the peaks come at some intervals. And you might want to understand when these peaks happen, because the energy spectrum, one of the things you get out of solving the Schrodinger equation is to get these energy eigenvalues, right? So Wigner could not, no one knows the Hamiltonian for the uranium nucleus, right? So does anyone know what Wigner did? Wigner solved this problem. So what he did was something actually quite clever, and I think has been extremely influential, not just in nuclear physics, but in many, many fields, including ecology, which is he said, look, uranium is really complex, man. I don't know about it. I don't know how to write the Hamiltonian. It'll be some matrix. I don't know what that matrix is. But I know that it can't be any matrix. It has to be a specific kind of matrix. Has to satisfy some properties, it has to be, for instance, symmetric. So he was like, okay, let me just replace this Hamiltonian with a random symmetric matrix. Okay? And then you can go ahead and you can find various things about the eigenspectra in this case. And it turns out that you can predict the spacings between these energy spectra perfectly if you use that approach, right? So what do we learn by doing that? Yeah, if you have a complex enough system, it's not maybe a bad idea that there's some things happening on in this complex systems, and it's complex enough that maybe those interactions or the parameters that you care about are random, but can they be any random parameters? No, right? They have to respect the constraints of the problem at hand. So, in Wigner's case, it was the fact that this matrix should be symmetric, so you can actually plug it into the Schrodinger equation. In our case, I mean, there'll be some constraints on what the interactions would be. Right now, it's not obvious to us. There can be some AIJs, right? But one thing that we learned is that, okay, we could think about filling these interactions maybe randomly, right? Does that mean that we can describe the exact soil system that we care about? Did Vigna actually describe the uranium nucleus? So actually it turns out, I mean, there was nothing about uranium in it, right? So actually any complex enough nucleus displays this the same energy level spacing distribution. So so in some sense, Vigna didn't just solve the uranium nucleus in that sense, he solved many of the other complex nuclei. So in this sense, also the price that you're paying when you're taking this random matrix approach is that you'll never be able to say something about any specific system completely. That, of course, you can't have a free lunch. You'll have, if you want to describe the system that you care about really well, you need to know about the interactions in that specific system exactly. And then you have to worry about a lot more things. For instance, you have to worry about whether the Lotka-Volterra model actually is a good description of that system, right? But if all you care about are statistical properties, then May, Vigna argued, and May was actually very, very inspired by what Vigna had done, that we can think about doing this for ecology as well, right? So we will get to this in about 20 or so minutes. But before we get to it, I now want to talk about a few other things, which are following what we talked about. That's feasibility and just linear stability. Any questions so far about the setup of the model and the sort of the philosophical approach that we are going to take soon? Okay, I'm going to assume that's a no. All right. Okay, so we have this set of equations for S species. And like we've been doing in this class, what's the first thing we should ask ourselves when we see a set of equations like this? We should ask whether there are any fixed points and what they are, right? So how many fixed points are, how many fixed points for a set of S species? Let's have a vote. For some given S species, let's say. Okay, is it A, S, 1? Okay, think about this for 5 seconds. All right, ready? 3, 2, 1. Again, if you don't know, it doesn't hurt to try. Okay. I would say most people are torn between 3 and 4. Okay, maybe you can take half a minute to discuss with each other what you think the answer should be. And if you don't have an immediate neighbor around, you just try and butt into another pair's conversation. Don't be afraid. All right, let's start wrapping up. Let's take a vote again. This was a good set of discussion, I think. All right, so if you have a given set of S species, how many fixed points do you expect? Ready? 3, 2, 1. Okay, I would say most people have converged to 4, meaning not 4, but 2 to the S. Okay, can someone give an argument for 2 to the S?
Not a great one, but in the last class we saw Lotka Volterra model with 2 species. Where
Yeah.
we had 4
Yes.
fixed points.
Yes.
So based on that, it should be either 4 or 5.
4 or 5? Oh, you need me option 4 or
option 3 also.
okay. That's
I thought it cannot be constant, or maybe, I mean,
The 4 fixed points was just for like the bistability and
there could be one, right? There are 2 null clines, they'll intersect somewhere. Yeah, it's just that fixed point was not feasible, right? Yeah, mathematically there are still 4. It's just one of them is not feasible, and that's going to be important for what we're going to talk about. Okay, so yeah, I would say that's not a bad argument, but it doesn't help us choose a unique answer, right? So does someone have more insight to provide to break this symmetry between 2 to the S and S square?
for each xi there were 2 solutions x1 equals to 0 or other versus 0. So
Yes.
for every xi there is 2 solutions.
Yeah.
Like that 2 into 2 into 2.
That's perfect, exactly, right? So for every species, it can either be extinct at some steady state, so xi could be 0, or it could be not extinct, in which case this thing has to be 0, right? So for every species, there are 2 options. All those species will, in principle, can have independent things happening. So 2 times 2 times 2 times 2, that's 2 to the S, right? So what does that look like? How does the number of fixed points look like with the number of species? It grows exponentially, right? Much faster. So should we start drawing phase portraits? Yeah, we probably can't do that, right? So we have to take a different approach, right? But we can see where all 2 to the S fixed points are now, right? You can now list them if you want it. You can iteratively set all combinations of species to 0. You'll get a bunch of null clines, etc., and you can solve it, right? Okay, great. And so what that means is if I take a set of S species, you can end up with a fixed point where not all of them survive at the fixed point, right? Some of them go extinct, right? Is it ever possible for all of them to survive and coexist? Yes, right? How many of those 2 to the S possibilities is that? 1, right? Why 1? Yeah, and so why is there only one way to make that happen? All are linear equations. Yeah, good. So how many variables and how many unknowns do we have? We have, yeah. So if all the species survive, the xi's cannot be 0 for any of the species, and that means you end up with a set of S linear equations with S unknowns, right? All of the S species abundances. And so there's only one way to make that happen, right? So there's only one fixed point where all the species survive, right? Okay, great. And what is that fixed point? Can we find what the steady state abundances of all the species at that fixed point will be? Sorry?
We liquid the bracket and 0 and
Correct. So we solve this equation 1 minus a x vector equals 0. Right? What's the answer to that?
x vector is 8 inverse 1.
Right? Okay, now two questions for you. Does this always exist? If a is not equal to 0, yes, it doesn't exist. Yeah. Yeah, a should be non-singular, right? What if a was 0? Then we know it doesn't exist. Can someone give me a quick argument for why a equals 0 should not work? It's the first thing we discussed in our first class.
So it's again
Exactly. If a equals 0, even your self-interaction is 0, and then you go back to a case where you grow exponentially forever, right? So that's the first thing that we studied in this class. That definitely shouldn't work, right? But there are other ways. Of course, a inverse cannot exist. If a inverse doesn't exist, then of course you can't say that, right? So that should exist. Okay, so let's say I choose an a. So now you see at least one constraint, right? One constraint that a should satisfy. Okay, but if let's say a is invertible, then are we done? Then is this fixed point always valid?
It should be positive.
Yeah. So this doesn't guarantee that all of the xi stars are positive, right? It does not guarantee that. Sometimes you might solve it and you can get an A matrix that when multiplied with this gives you some negative entries, right? And in that case, that fixed point exists, but it's not feasible, just like this case where we had in the two species situation where the null lines didn't intersect in the first quadrant, right? So if you want this fixed point to be feasible, you must choose your A such that it's invertible and satisfies that property. What if it didn't satisfy it? Then if you put all the species together in some mixture and ran these dynamical equations, what would happen? Some of them will go extinct, and whichever ones survive should satisfy something like this, right? Will they satisfy exactly this? Let me repeat what I was saying. Say you throw in S species. Each of these nodes are one of the S species. They interact with each other in some way. This is just a representation of my Aij matrix, right? I'm not going to draw all of the links. I throw all of them in, they start interacting, these dynamics start happening. We know, we did this math, then we know that not all of them can coexist at this final fixed point because it's not feasible. Some of them will die. Let's say this one dies, that one dies, that one dies, that one dies. So now what we are left with is this set of species. What's the coexistence fixed point for that set of species? Let's say these species labels are 1, 2, 3, 4, and 5. And 6, 7, 8, and 9 went extinct. How do I find that? I can't find it using this anymore, right? Why is that? Some of the entries will be negative.
From the initial equations, make the thing 0 and
Yeah, okay. So you're saying that I should choose I already know that these things are going to go extinct, so they should not be part of the linear equations that I'm trying to solve now, right? So now you get a reduced set of linear equations only for your surviving species. Would those interact using the same matrix? A sub matrix of that, right? And in fact, the way I chose this, it would kind of be something like this, right? This is the first 6 species here, the first 6 species here. All of this you should throw out.
How will we know which species go?
Wonderful. Yeah. How will you know which species go extinct? You will have to know. Yeah. One trick that often seems to work, though it has no reason to, is that you can start with, you can do this process iteratively. You can first guess that all the species survive, find the fixed point vector, see that it's unfeasible, take all of the species for which the xi's are negative, throw them out, take now the reduced matrix, I can call this A reduced, find xi star reduced only for the set of species that you now have, which is what? A reduced inverse times 1, 1, 1, blah, blah, blah. And then keep doing that until you get something that's feasible. So that often works in practice.
This could be done for any of the other fixed points also.
This can be done for all 2 to the s fixed points. Because there are 2 to the s different ways of taking subsets of this matrix. Yeah. So yeah, if you knew which fixed point you are looking for, you just need to ask which species survive, which species go extinct. Once you pick that, the fixed point is unique, right? And that's how you find it, right? So it's true that there are 2 to the s fixed points, but a smaller fraction of them may be feasible. Only a small fraction of them might be feasible. So not all of them are feasible. Okay. All right, so we talked about fixed points. We talked about which fixed points we should care about. We should care about the feasible ones. What's the next thing that we talk about in the course? What did we do for 2 species and 1 species? We asked for stability, right? So let's say you went ahead and you found some feasible fixed points. How would you say something about stability? Someone in the back? Did we not do any stability analysis in this class yet? Sorry? You do a perturbation around what? Yeah, so you perturb all the species around some fixed point that you care about. And then what do you do? Exactly. Yeah, so you look for the dynamics of the perturbation, and you ask whether some Jacobian that you care about has eigenvalues which have negative real part or not, right? So what's the Jacobian in this case? So we're talking about dynamical, in particular linear stability. You want to take d dt of some xi star plus some epsilon I vector, right? And what's that going to be? You're going to plug that in over here in all of your equations, right? So that's going to look something like xi star plus epsilon I times 1 minus xi star minus epsilon I minus aij xj star plus epsilon j not equals I. And you can work through this, use the fact that epsilon is small compared to 1, and compare to xi star in fact 2, and you can arrive at the following Jacobian. You'll see that d dt epsilon I will be essentially something that looks like the following. Can you check if I wrote it correctly? So this D is a diagonal matrix with all of the xi stars put in. A is, of course, the A matrix, the full A matrix. And that's our epsilon vector, that's our perturbation vector. This is a linear equation, right? The same way that we've been dealing with. This whole thing over here is our Jacobian. Right? And it has two parts, right? One is this diagonal matrix with all these fixed point abundances, and the other is your interaction matrix. Okay, so how do I say whether things are stable or not? Find the eigenvalues of the Jacobian, right? Correct. There's this A matrix sitting here, right? The A matrix is also a square matrix. It'll have some eigenvalues itself, right? Is there some connection between the eigenvalues of the interaction matrix and the eigenvalues of the Jacobian? Should be related, right? The Jacobian has the interaction matrix sitting in it, right? This diagonal matrix only has positive entries sitting on the diagonal, right?
The eigenvalues of matrix A should have a negative real part.
The eigenvalues of the matrix J should definitely have a negative real part, right? What about A? Yeah, so why should the eigenvalues of A have a negative real part?
It can be stable or
So this we agree, right? The actual eigenvalues of things that we care about is J, right? But in many cases, because all of the entries in this diagonal matrix are positive, not all cases, but in many cases, and I think this was in your reading something about D stability. There's a mathematical property called D stability, which has to do with finding some sort of diagonal matrix, where in fact it's true that if the only thing that you care about are the signs of the eigenvalues, the signs of the eigenvalues of A and J will be very closely related. And especially if A is a symmetric matrix, the signs are exactly the same, right? So just a thing for you to appreciate and remember, we always care about the signs of the Jacobian, or the signs of the eigenvalues of the Jacobian. In many cases, but not all cases, the signs of the eigenvalues of the Jacobian and the signs of the eigenvalues of the interaction matrix are the same, right? And so there's this really cool thing where, oh, if you choose your interaction matrix a certain way, you can already set up the system to be unstable, right? This is a subtle point. If you ever forget it, that's totally fine. You should always be able to get from these equations to this equation, know the right Jacobian, and be able to say the correct thing about stability.
So, we first choose an A that satisfies the other conditions for A.
Correct. Yes. Yes.
Then we proceed to this, right?
Correct. Exactly. Very good. Yes. So, of course, there's no point in talking about stability for a fixed point that's not feasible, right? So, yeah, the first property you need to satisfy is that you need a feasible fixed point. In fact, this whole thing you do around that feasible fixed point, right? You can't do linear stability in abstraction. You have to choose some point around which.
So we are not doing it for any general stable point. We
Well, we don't know about stability over there. We are only knowing about stability here. So you want to choose a fixed point that's feasible, and then ask if it's stable or not, right? What we've been doing in the last few classes. First, we find all the fixed points, then we go and ask how stable each one of them is.
So these xi stars are for the coexistence.
Yes, exactly. These xi stars are the fixed point you are querying the stability of. Great, yes.
So if you are considering at least minimum 3 species,
Yes.
and there's a possibility of chaos coming in,
Yeah.
and will this method be able to get any insights?
So if you have chaos, you have no fixed point per se, right? Well, you can have fixed points, but you know your dynamics, you probably don't care about that fixed point so much. So here you're correct that what we're assuming is that the behavior that we have is that the system eventually goes to some fixed point, right? I'll come to chaos towards the end of my class, but for now what I'll say is for 3 species or 4 species or something like this, the chance that you'll pick a random matrix A that will have chaotic behavior is of measure 0. You will have to work really hard to tune the parameters exactly correctly to get chaos. And if you disturb the parameters a little bit, chaos will be lost. So that's so the mathematical statement there is that the chaos is not generic for for low dimensional systems. It becomes generic for high diversity systems. I'll come to that by the end of the class if I haven't reminded me. Yes.
Why did you say for all cases we don't care about the
For all cases, we don't care about the eigenvalue. Well, I said that if your fixed point x star is not feasible, then you don't care about the Jacobian around that fixed point, right? That's what I meant. Yeah. Okay, good. Final comment about this kind of stability. This stability is often in ecology also called local stability, as contrasted with global stability. Can someone tell me why we say local stability? Yeah, what you're saying is that yeah?
There can be other stable points, so if your particle is near there.
Exactly, right? There could be, we agree that there could be many feasible fixed points. And again, not all of them might be stable, but some of them might be stable, right? So in principle, there could be cases where there are more than one fixed point, more than one stable fixed point. And what we are assaying for here is that fixed point that I'm looking at locally stable or not? If I make small perturbations around that fixed point, will I come back or not? Right? Kind of think about this picture. If you had 2 stable fixed points, all we are asking is if I'm sitting here, if I make small perturbations, will I come back or not? Right? Of course, if you make a large enough perturbation, you might go to another stable fixed point. Right? So there's also this notion of global stability, which is the question of asking, okay, if you just threw the system with random initial conditions everywhere, what fixed points are you most likely to go to, right? And there can be some cases, especially, where there is only one globally stable fixed point. There is no matter which initial condition you choose, you'll always go to that one globally stable fixed point. But that condition is not always satisfied. So that again, I'll come to towards the end of the class if I get any time.
Why should it go finally to it? It can do those oscillations.
Yeah, we're coming to that. Yeah, so for oscillations, remember you need to get an unstable fixed point, right? So this is only when you have stability. And yeah, we are just asking what it would take to get the stability, right? We haven't said what's the likelihood of things being stable or not, right? But okay, great. Let's talk about that exactly now. Right, so I think now we are kind of set up to talk about May's argument and what is called the diversity stability debate. Yeah. Yes. There can be only one stable fixed point. They can be other unstable fixed points. Okay. Yeah, so we already talked about the fact that if we have S species, we have lots of these parameters, these S square parameters. We don't typically know them. We haven't thus far said anything about random matrices. We've just been saying, oh, if I had a matrix this way, this is the constraints it would need to satisfy, right? So now we're going to talk a little bit about this. What's the consequence of thinking about random matrices? So this is what's been called in ecology a lot as the diversity stability debate. And if you don't see why it's a debate yet, hopefully you'll see by the end of today's class. And this is due to May 1972. Okay. So May was trying to say something about how likely it should be that a given ecosystem with S species can be at some stable fixed point or not. Okay? And like we said, he wanted to first ask, okay, what should I do to parameterize this matrix? Right? So he chose this thing where there are S species. And he said, let me make a random S by S matrix. But not any random S by S matrix, right? So the thing that May really did was to come up with a recipe, right? And it was a recipe to build some random matrix. The question is, which recipe did May come up with? Did he come up with a recipe for A? Ready, 3, 2, 1. You all did the reading, right? So did he come up with a recipe for choosing A or something else? So he did not come up with a recipe to build A. He actually came up with a recipe to build J. So this J is also in May's paper called, confusingly sometimes, M, and it's called the community matrix. So actually, if you go and read May's paper, which I think is just 1.5 pages or something, actually I think it's just 1 page. It kind of starts off by just saying, okay, consider a feasible community with S species, right? So what he's saying is, I already have the thing that's often hard to do, right? You have some A matrix that you chose that gives you some feasible state where there are S species surviving. And now he wants to build this community matrix M as a random matrix. This is a recipe for M. What's the recipe?
1 minus C probability 0 and C probability takes.
So first of all, this M matrix, looks like that, right? Did he have the same recipe for all the entries of the matrix? Yeah, so there are 2 different parts, right? There's one part to set all the diagonals, and then one part to set everything else, right? So one part is for what I'll say MII, is the diagonal entries. What was the recipe here?
First, you're assigning whether the interaction exists or not. So you're picking with some probability whether each non-diagonal element is 0 or 1.
So let's just talk about the diagonal entries first. What's the recipe for the diagonal? Can the diagonal entries, can some of them be 0? Is that possible? What would happen if some of them were 0? You would have no self-limitation, you would have no growth, right? This is again going back to the first thing that we did in the class. So all of the entries have to be non-zero here, right? And in fact, did May assume that they're different for different species? No, he didn't. He assumed that they were all the same. Some number, I don't have to say minus, some number d, right? That d has been 1 so far in what we've been talking about. But he was like, it can be any strength that you choose, some number d, right? This is the self-limitation.
But why should it be the same for G?
Why should it be the same for all the species? Yeah, good. That's an assumption. You're saying it could have been D for one, E for another, and so on and so forth.
But that was in the matrix A.
Yeah.
They're constructing the matrix J, so which is multiplied by the abundances of the fixed point.
Correct.
So that might change the.
Correct. Yes, that's completely true. So this is one of the sort of weird things about May's paper. But to be honest, qualitatively it doesn't change anything. You'll see that this argument that he gave, the reason it's so influential is not because something about his recipe was kind of off. It's that modification to this recipe gives you the same behavior, right?
So it doesn't really matter if we follow this recipe to make J or A?
It doesn't really matter if you follow this recipe to make J or A. Yeah.
As long as D has positive type.
Which it should, because you're only considering feasible things. Yeah, qualitatively. So let me just tell you again where we're going. I said in the beginning of the class, what May showed was that when S becomes large enough, you will generically go from this fixed point being stable to becoming unstable. More species means unstable, which was really funny because, well, we go out there and we see more species. Okay, so that's kind of where we're going in the next 20 minutes.
Is there any deeper reason for this interchangeability between A and M?
There is a very deep reason. Yeah, I'm not sure I'll be able to go into it in the class, but come to me after class and we can chat about it. Yeah, this result is more than 50 years old, so people have thoughting about it. Okay, so that's it. That's a recipe for the diagonal bits. Then there's the off-diagonal bits, right? What was the assumption about the off-diagonal bits?
First, we have seen whether there's an interaction or not. So 0 and 1, and we pick it with some probability, say C.
Yeah.
And then you multiply each of those terms with another random variable, which is chosen from some distribution. And that distribution should have a mean of 0. And I think the values can be significant.
Yeah. So what he assumed, and this is one recipe, we're just talking about what May did, but a lot of these things are going to be robust to different choices, is that he said, well, okay, all species have to self-inhibit themselves to have some carrying capacity, but okay, some species may interact with each other, some species may not interact with each other, and in particular, there would be some connectedness in this graph of interactions between species. That connectedness can be 1, in which case all species interact with all species. It can be 0, in which no species interact with no other species. It can be some intermediate number, half, where half species interact with other species. And so with probability C, which is the connectedness, you pick some interaction between these species from some distribution that you like, right? And what May chose was a Gaussian distribution with 0 mean and variance sigma square. And we'll see it's really the variance that we're going to care about. This whole argument is a variance argument. So don't worry too much about the mean. The mean is 0, say. It just makes things mathematically easy. Okay? What's going to be so this is Aij. And what's Aij going to be if you pick the number and it's, with probability 1 minus C, you get that they don't interact? Then Aij is 0. Okay, question again. Are Aij and Aji going to be correlated? No, right? By this recipe, they're not going to be. In fact, Aij might be some non-zero number, and AJI might turn out to be a zero number, right? Everything you're picking sort of randomly. Yes?
Is setting the mean to zero just helpful in math, or does it, like if we say mean is not zero, does it mess up the circuit law?
No, it doesn't. It doesn't mess up the law at all. Yeah, this is purely a mathematical convenience. Okay, so that's the entirety of May's algorithm or recipe. Just to make things concrete. Okay, and then what did May care about? Then of course we have been talking about J, and we've been talking about the eigenvalues of J, right? So how many eigenvalues does J have? S, right? If there are S species, it has S eigenvalues, and as S becomes larger and larger, there's more and more and more eigenvalues, right? So, and how many eigenvalues are there when S goes to infinity? Infinitely many, right? So can we actually go and count all the eigenvalues? No, right? So typically in this case, what do we do? Yeah, so if S goes to infinity, if you have an infinite size system, then you start talking about a distribution of the eigenvalues, right? And that's something that we can call an eigenvalue distribution, or often an eigenvalue spectrum, or an eigenspectrum, right? And so what we really care about is the eigenspectrum of M. Okay, and so since we're talking about eigenvalues, I'm going to draw the complex plane. So that's the real part of any eigenvalue. That's the imaginary part of any eigenvalue. Where do we want to be for things to be stable? Do we want to be, okay, let's vote. Do we want to be on the left, point up? You want to be on the right, point down for stability. Okay? Ready, 3, 2, 1. Yep, we want to be on the left, right? So that region is a stable region. You get stability. That region is a region of instability. Okay, and now we need to start counting all of our eigenvalues and putting them in, right? Is there something statistical I can say about the eigenvalues? Thus far in the class, we've been talking about two numbers about this matrix that should tell us something about the eigenvalues, right? What are those numbers? The trace and the determinant, right? So what does the trace tell us? Yeah, the trace of M tells us about the sum of the eigenvalues, right? That's I going from 1 to S. Right? What's the trace of May's matrix? D times S, right? What about the mean eigenvalue? That's a trace divided by S, right? So that's SD divided by S, and that's just D. Why did we calculate the mean eigenvalue? Right, so there's some distribution of eigenvalues. The mean tells us where the rough center of that distribution should be, right? And strictly speaking, this actually remember the J has this sign. Since everything has a negative sign, this is actually going to be negative, right? This is self-limitation. The eigenvalues corresponding to it are going to be negative. So this is going to give us a mean eigenvalue, which is minus D. Do people agree? I'm just trying to tell you, just think about all of the entries being 0. When you have self-limitation, all of the species stably inhibit each other, right? So in that case, all the eigenvalues should be negative and all should be minus D. So that's sort of where we are. we should be stable, right? And in fact, if C was 0, that's where all of the eigenvalues would be, right? So now what we want to start doing is to start increasing the connectance a little bit, or you can have C1 and sigma square equals 0, right? Okay, so this mean eigenvalue is the first argument that May has, which is that this is the center of the eigenvalue distribution.
We got
Yeah, but there's actually a minus sitting some. Well, okay, if you're filling in M, then actually you should put in a minus D over here, because the Jacobian contains minus terms, right? So you can, yeah, if this makes it easier for you. Okay, good. Now we want to care about all of the other eigenvalues, right? They won't always be degenerate, and in fact, when there is going to be a non-zero sigma square and a non-zero C, they're going to be in different places, right? So this is sort of where one of these famous properties of random matrices come to save us. So there's many things about random matrices and their eigenspectra that we can actually calculate. And if you were interested, then you can take mathematics courses about random matrix theory. It's a well-developed field. Okay, but there's one very nice result called the circular law, which I think comes due to Guillebre. It's very old. It's like 150 years old, which says the following. Yeah? It says first thing that you need is an S by S non-symmetric matrix. Do we have that? It's not symmetric. Aij and Aji don't have any relation between each other. Okay, satisfy that. Second thing that we need are IID coefficients. Do people know what IID is? They're independent and identically distributed. We have that. Right? And in particular, this law is for one where the mean is 0. You expect, the x's, which are going to be all of the entries of this matrix X that we care about in the circle law. The expectation value is 0, the mean is 0. And sorry? Mean of x squared is 1, correct. Okay. In our case, we don't have that, right? We can account for it in a second. And it's valid when S goes to infinity. Yeah, that's also something that we'll care about. We'll care about cases where there are large matrices. Then it says the following. If these conditions are satisfied, that the eigenspectrum, the ESD, the eigenspectrum distribution of X by root S is a circle with a center at 0 and radius 1. Good. I'm not going to go into the proof of this. You can read about it if you're interested, or come to me later. Okay, so in our case, we don't have this, right? Because we didn't satisfy these properties. But we can always scale our matrix to make this happen, right?
This means outside the circle, the probability is.
Yes, outside the circle, as S goes to infinity, all the eigenvalues are confined to a circle, right? So if you have something like this, all the eigenvalues are going to sit inside that circle and nothing outside. This is nice, right? So in our case, or May's case, we can always, of course, scale out the mean. That is just going to give us a center. At the mean is just setting where the center is. The only thing that we really need to care about is this second moment bit, right? So in our case, what's our E of m square? It's not 1, right? It depends on these entries. So it's something like C sigma square. Right? Not all of the entries are going to give you a sigma square. With probability C, you're going to get that. Right? And so in our case, we'll actually get an because of this, we'll get an ESD of X, or in our case, M over root of S times root of C sigma square. Right? That's just a scaling, and this part is going to be a circle with radius 1. And so if you wanted to care about the full thing, that's going to be a circle with radius what? Root SC sigma square. Right? So in our case, what we end up with is a circle with a radius root SC sigma square. Yeah?
We are taking Gaussian distribution.
Yeah, we're taking a Gaussian distribution. Oh, yeah, good. Yeah, go on.
So there might be slightest probability that it lives outside the circle. The eigenvalue might live outside.
Yeah, but in the S going to infinity limit, actually the circle law will prohibit that. Yeah. So and actually this circle law didn't say anything about the distribution, right? So actually you could choose any distribution that you want, right? This property is called universality. But the exact distribution that you have doesn't really matter. This circle law is true for any distribution that you choose. Okay. So, yeah.
So what did you write ESD of?
This X over root S. So
What does it mean?
okay, good. Yeah. So remember, if the size of the matrix becomes infinity, the trace of the matrix becomes infinity. So the mean eigenvalue also becomes undefined, right? So you need to scale something about the matrix to get a well-defined set of eigenvalues, right? So you can just scale it by root S. That's just what the circle law is saying. Yeah.
You're multiplying the distribution with this eigenvector distribution with this.
Yes. Yes. Yeah. You're multiplying every entry of X, every entry that you get from the distribution, every sample by root S. Then if you scale it, then you'll get things that are well defined. Okay. So now that's kind of nice, right? We now know that all of our eigenvalues when S goes to infinity are going to roughly sit inside this circle with a center minus D and a radius of this, right? And in a circle, these are the only two numbers that we care about. We care about a radius and we care about a center, right? So is anything going to happen to the center as the number of species is going to increase? No, right? Remember, we want to ask what happens as the number of species increase. Is anything going to happen to the radius as the number of species increases? Yes, right? Will the radius increase or decrease? Ready? 3, 2, 1. Okay, great. It'll increase, right? And if you fix C in sigma square, it will still increase, right? So for any given C in sigma squared, you can start off with a small number of species and the radius is small. You have more species, gets bigger. At some point, does something special happen? It just touches this y-axis, right? There's some critical S at which that happens. What's that critical S? This radius becomes equal to the distance from the center, right? This d, right? So root of S C sigma squared equals d at this special point. That's how many species, if you care about S as S critical, that's the critical number of species at which this will happen, right? So you can calculate that exactly. That will give you S, which is d squared by C sigma squared. Yeah, S critical, right? So there's a critical number of species that you add, after which if you add more, the system generically becomes unstable. Yes?
How are we interpreting the circle when S is finite? Because the circular law only works when S is
Good, yeah. So it's completely true. So the way you're interpreting it, and you should try it out on your computers as well. You can implement this. You know, it's an algorithm for a reason. You can actually go and implement it. You'll see that, yeah, when S is finite, then of course, strictly speaking, it won't be a circle. Some eigenvalues will lie outside it, which only means that it can become easier in finite systems to break stability, right? Just by chance, sometimes even when the circle has a radius that's smaller than this d, sometimes by chance you can get an eigenvalue that's outside it. But still, statistically, it's true. It'll become easier and easier to get an instability as you add more and more species. And but the circle will still, you will still largely be able to see the circle. If you actually go and try this, plot all the eigenvalues, plot this radius, you'll see most of them lie inside. And you might have seen it in the reading itself. In the reading itself, there were some simulations, right? That worked pretty well. Yeah?
still weird because the circular law is
Correct. So this is actually true for all things that have to do with the central limit theorem, which is that basically these things are all exact for when things go to infinity, but in practice, 10 or 20 is infinity, practically. So that's why we love these kinds of theorems, right? Because they work even in practice. Yeah, if you actually had to rely on things going to infinity, then it would be a problem. Okay, so this prompts us to draw something. Which is the following. So now what you can do is you can plot the number of species on the y-axis, and you can plot maybe even the complexity or the connectedness of your ecosystem on the x-axis. This is C, this is S. What conditions need to be satisfied for this system to be stable? Yeah, so for a fixed sigma square, SC should be less than some constant, right? What is that an equation of? It's the equation of a hyperbola, right? So there's some hyperbolic curve here, which is SC equals, d square by sigma square. And what happens on either side of this boundary? You either are stable or unstable. Okay, quick question. Are you stable up or stable down? Ready? 3, 2, 1. Stable down, right? These are all things that are stable. These are all things that are unstable. So now there are two ways of slicing this that are fun to think about. One is you take ecosystems with the same level of connectedness, but different numbers of species. Right, that's what we were just talking about there. There's a certain number of species at which things become unstable. You can do the other thing as well. You can take different ecosystems with the same number of species, and you can ask when they become stable or unstable. And what does this say? What do you need to do to make a large ecosystem be stable? Yeah, you essentially need zero connectedness, right? Which means no interactions at all, right? So this is making this stark prediction that if you want diverse ecosystems that are stable, you actually don't want them to be interacting at all. That's not true, right? We see species interacting out there. Or do you think that may change your mind now? Species should not be interacting. Yes?
From a very ecological point of view,
yes.
If you add a species, your sea completely changes. So sometimes it's kind of a disconnect to kind of the equations that you have.
What do you mean? What's the disconnect?
Let's say you add a species.
Yeah.
Your connectedness completely changes once you add a species, because in the ecosystem you have rearranged the connectedness that are the way they are interacting.
You rearrange the abundances, right?
Even the way they are interacting also changes.
I mean, what you're doing is you're adding another species. So you're adding another row and column to this matrix of interactions, right? Yeah. And sure, yeah, because of that, the system will rearrange, right? And it's true that we haven't incorporated that bit into this setup, right? It turns out you can incorporate that as well. So what we aren't going to do in this module, because we're going to end in 5 minutes, is that you can now do a different set of calculations where you exactly ask how do you build an ecosystem one by one. And there you can also show that generically that system can become unstable in very much the same ways. Okay, so yeah, I'm not going to do it here. Sorry, I can send you some references if you're interested, or come take my course next year. Yeah, that thing that you're saying survives. This argument about the stability and instability survives that way of building a system by adding in invading species one by one. Yeah?
I didn't quite get the point.
I think his point is that here we are imagining that there's a fixed number of species, they're interacting in some way, and so they're stable or unstable. But in any real ecosystem, new species will be coming in and doing all sorts of things. Did I understand that correctly? And so where is that? Yeah, and so where is that? It's not here. Yeah.
I was just thinking, C completely changes, then maybe the circle may not.
C won't completely change. See, like when you have a large number of species and you add one more thing, C is not going to completely change. It might slightly change, right? But C won't completely change. You won't go from C being 80% to 10%.
So there's in ecology, there's something called as keystone species.
Yeah.
Kind of concept.
Yeah.
Like if you change one,
Yeah.
add that one,
Yeah.
completely connected.
No, the connectedness doesn't change in the case of keystone species. What happens is that the presence or absence of the keystone species renders many species extinct or not extinct because of the interaction that it has. So the surviving species may interact differently. But when you have keystone species, it doesn't change the statistical properties of the interactions. It just goes and kills or doesn't kill a set of species, which can be large. Yeah, we can chat about it offline if you're interested. Yes.
Regarding this,
Yeah.
introducing keystone species, is it like adding 3 body? I mean, it's right now 2 body interactions. If you had 3 body interacting, in a sense, 3 species.
Yeah.
Is that what effectively, I mean, they're interacting?
Okay, you're talking about what we call higher order interactions, where you have growth rates which are now quadratic in species. I mean, again, you could think of it that way, but typically in keystone species, you don't need to think about it in that way. You can just think about, some special species that interacts very differently or very strongly with all of the other species compared to all others. like think about some apex predator or something like that. Okay, I have 5 minutes left, so I'll try and wrap up and then I'll open it up for questions. I just want to discuss about this instability for the next 5 minutes. So for the longest time, people were puzzled by this. And in fact, if you saw your reading, actually, there's many modifications that you can make to the same basic recipe. You can imagine correlations between the interactions. You can lots of things. You still have a stable region and an unstable region. That's why people have been really puzzled by this, right? Because it makes this completely counterintuitive assumption, right? But it's actually really surprising that until maybe like about half a decade ago, people didn't really, this was treated as some sort of forbidden zone. Here be dragons. You're not supposed to go here. What do you think? I mean, you can still build a system with S species and connectedness C that sits here, right? What do you think happens to the dynamics here? What is May telling us? Sure, there's a feasible fixed point where all species can survive, which becomes unstable. Something else must happen, right? When we were talking about feasibility and we said all S species don't survive feasibly, we said, oh, some species go extinct, right? So what do you think happens if you actually try and simulate a system in this region? There's nothing stopping you from running the dynamics, right? Yeah, so one of two things happen. So what we just did is a stability analysis of some feasible fixed point where all species survive. That one we showed will generically become unstable. Yeah? Now, two things can happen. In a finite size system with a finite number of species, even if that's large, typically you get other stable states where this doesn't happen. Why? Because some species go extinct, S goes down below S critical, and that fixed point can be stable. Okay, this is just a statement of saying you can't have a stable fixed point with more than S critical species. You can have one with less than S critical species. So that's one thing that can happen in this region. This is just the instability of the full state with all S species. The other thing that can happen, which happens much more generically the more and more there's diversity, is that all fixed points become unstable. And instead, you generically get chaotic behavior or oscillatory behavior. Okay, and that's the only generic oscillatory or chaotic behavior that you see in these kinds of models. Okay, so again, if you take my course, you'll see that you can spend time sort of studying this region and describing what that chaotic behavior, what those chaotic dynamics look like. Right? We're not going to talk about that in this class, but I just wanted to give you a taste of what that is. Right? If there are 3 species, it's very, very hard to get what is called generic chaos. You have to really choose your parameters carefully. If there are like 100 or 1,000 species, yeah, even random parameters will give you some behavior that's either oscillatory or chaotic. Yeah, so you can try this out and play with it yourself and see that these things happen. And this is very much some of the things that people study nowadays in theoretical ecology. This brand of ecology, which we like to call high-dimensional ecology or ecology in high dimensions. Yeah, so that's kind of the end of this module. Yeah, I'll take questions. Brato will also have some announcements for the next module. Yeah, I hope you learned something about ecology, 1 species, 2 species, many species. And yeah, there's lots of resources to read more about this if you're interested. Yeah, thanks. It's been great teaching you. I'll take questions. Yeah.
Even if S is greater than S critical,
yeah,
more than half of the circle lies here.
Correct, but remember for instability, even if you find one unstable eigenvalue, that's going to dominate a long time, right? So yeah, this is often a thing that can be confusing. Well, all of these things are stable, but at long time, the unstable thing's going to kill you. Yeah. Any other questions? What happens at S critical? Yeah, can you tell me?
I don't know.
So what is the largest what's the eigenvalue with the largest real part? 0, right? So did we study a case where there was a, what did we call it? It wasn't stable or unstable, right? It was neutrally stable, right? So you get neutrally stable things. The perturbation will neither grow nor die. You'll have some direction in this space where you can walk without a cost. So you will also get neutral stability here. Some people call neutral stability marginal stability. It's the same thing. Okay, we can take more questions, especially you can come to me afterwards, but a couple of quick announcements about the rest of the course. So next week, there are no classes. We will resume the week after that. The first class is on the 11th, right, Brato? 12th, okay. Sorry, the next class is on the 12th of June, and that's going to be Brato's module, and Brato has, I think, a few questions. Yeah.
So,
You can use this.
Hello. So a couple of things. First is that, like Akshit mentioned, next week no classes. What I will cover is essentially what you can call is biological fluid mechanics. So there are two pieces of what I will cover. There is one piece is mechanics and fluid dynamics, hydrodynamics, and one aspect is, of course, applying those ideas and concepts to biological systems. So what I would do is that I would like to take a quick poll of how many of you have done some sort of classical mechanics courses, some exposure to classical mechanics. Okay, that's great. Have you done any sort of fluids ever? Okay, some people have done some sort of fluids as well. Okay, great. So what I would do is that based on this, I will maybe try to send you a couple of things to read about. Nothing technical, just to get familiar with some words of fluids and other things. And there is a very nice video lecture, which I will go through in depth. We'll cover all the topics of that lecture, but it's available on YouTube freely. So I will just send it to you. Take a look at it. It's like 20 minutes lecture. It's by a very famous scientist called G.I. Teller. And you will get to see sort of what is the world that I'm going to talk about. Okay, I think that's all I wanted to get a sense of. Thank you.
Yeah, if there are any questions on Zoom, I'm also happy to take them.
Hello, sir. Can you hear me?
Yes, I can. Go ahead, please.
Sir, actually, my question is that, as you said, that there is only one possibility in which all the species can coexist. So, does that actually means, can I correlate that concept with the concept of this absolute zero temperature in statistical mechanics, where there is zero entropy?
Why would you want to think about it that way?
As you said,
I mean, you're right that there's no noise in any of these equations that we're talking about, right? So it's kind of like a system at zero temperature, but yeah, why do you want to think about things like entropy?
No, means if I can correlate these two things, then it might be easier for me to actually make sense out of this biological systems in terms of physical systems.
Okay, I would advise being careful about that, because often your intuition about stat mech might be coming from equilibrium statistical mechanics, and studying about biology is exactly the opposite of that. It's about studying systems where you want to care about non-equilibrium statistical mechanics, and often your intuition that you're trying to import might fail you.
Okay, sir.
How do the predictions of this model hold up with the field experiments? We see that there are connected species. I mean, very strongly interact with species, but and that goes through the large number of species.
Yeah.
This is exactly opposite of that. So how do
Yeah. So like we said in the beginning of this class, it's actually pretty hard to estimate connectedness itself, or it's pretty hard to estimate interactions in a large real system. That being said, actually last year there was a paper which actually tried to do exactly this kind of diagram that I was talking about. So there's a number of species on the y-axis and the connectedness on the x-axis, right? So these authors had a way of computationally trying to estimate the connectedness in the number of species. This sort of hyperbola that I drew. They went to some communities and there they tried to actually measure S and C. Okay, and what they're trying to say in this paper is by no means should be taken as, oh, this is absolute truth, is that they find a bunch of points from different ecosystems that kind of lie here. So what they were trying to say, so this is all real data, and what they were trying to say was that, okay, maybe May is not so bad. So
biology, we might say that there might be some subgroups which have higher C compared to the others.
Correct. So yeah, you can imagine.
Is it something like that? Or
no, so you can then make a modification to May's recipe where you have block structured matrices. And then, I mean, of course, just the qualitative thing is, of course, there's a number of species beyond which things become genetically unstable. Just when exactly that happens, what exactly this boundary is, that can change quantitatively. That's sort of the power of May's argument. There is a stable region, there's an unstable region. Yeah, based on how you choose your recipe, you'll change this, the way this curve looks. That part is, yeah. And yeah, the main point is, it's not like the unstable regions here, the stable regions here. It's always the things become unstable at large diversity. Yes?
In the model, we've assumed that all the connectedness, like all the interactions have the same weight. So what if
All the interactions have the same weight.
Yeah, I mean in the sense like, what if some interactions are stronger than others?
That is already allowed, right? In the sense that, yeah, so you can have this, right? So you have the AIJs essentially picked from some distribution with some Z, right? And so some can be here and some can be here, some can be here. Yeah, so that's already here.
Someone online asked the name of the textbook. You could send a link.
There's no such textbook. This is a textbook that is in progress being written, and I've shared with you rough drafts of it.
I had a question.
The person on Zoom, I'm sorry, just a second. We are listening to a question here, and then we'll take your question.
Are we assuming that the species are the same size scales in terms of the?
You're saying how do you define a community, right?
Work out and say human enclosures, not human enclosures, but like zoos or like sanctuaries where you kind of limited.
Okay, good. Yeah, so the question is, how do we really define a community, especially when things are open, and how do we compare it to zoos and enclosures and so on and so forth, right? Yeah, so, generally the question of defining where a community starts and where it ends, it can be a bit murky. There's some cases in which it can be more clear and less clear. For instance, you might have heard of these human gut microbiomes. Inside our guts, there are these microbial communities, and then mine is different from yours, right? Those are definitely distinct communities. In the soil, it actually is notoriously hard because there's just grains of soil and so on and so forth. So one way that we often think about it in ecology is that you can think about different patches in which there are different communities that are all connected to each other. How do you define one patch from the other? That depends on migration, mixing, and so on and so forth. So if there's a length scale in the problem where mixing is much larger within that length scale and less beyond that length scale, that gives you sort of a rough way to define a community. In the oceans also people do that. Yeah, go ahead. Yeah, usually some spatial thing. Yeah, and in zoos and stuff, again, you can imagine that, yeah. Yes, there was a question on Zoom.
Hi, am I audible?
Yes.
So about the diversity stability debate. So you mentioned something about how ecology models do not take evolution into account and vice versa. How much do you think that plays into account into the debates?
So, like I said, people haven't really thought about evolution in this context yet. What would evolution mean here? One thing it could mean is that these AIJs change over evolutionary time, right? So you can do an evolutionary version of this whole thing where you have some species, they're stable, they have a mutant that comes out of those species which has slightly different interactions with the rest of the community. You can ask whether that survives or doesn't survive, and you can keep doing this process again and again and ask what happens. No one's done this yet.
I also had another question.
Yes.
Also, with respect to how well this debate fits with the experimental data, you mentioned a statistic as to how many species 1 gram of soil has.
Yeah.
But I would, how much can you say about the stability of those species in that gram of soil?
That's a great question. That is a great question. That itself is very much debated, I would say. How stable is a community out there in nature is generally hard to answer. That being said, what people have been able to do in the last decade or so is to bring a lot of these natural communities into the lab where you can control conditions and observe dynamics. And there what people have observed generally is that when the number of species tends to get very large, you tend to get dynamics that don't settle to a kind of stable fixed point, but instead tend to show these persistent fluctuations of the kind that are consistent with this chaotic behavior that you might expect. So that's one way that we know it.
About that evolution.
Yes.
If we write the coefficients of the matrix as functions of time, or each
Yeah.
of the coefficients
Yeah.
as some function of time,
Yeah.
and all of them are different. So would that kind of be on the right path?
It could be one way, but remember that the thing about evolution that makes it difficult to study is that there's a feedback, right? If you're defining all your A's as a function of T, that means you already know the trajectories things are going to take. But the whole point is there's a contingency of what evolves first, what that does to the rest of the community, what path that community takes that you won't know a priori. So you'll have to put in some complex feedbacks where all of the AIJs depend on all of the other AIJs and on the state of the community, and they're all co-evolving with each other. That's what makes the problem hard. You don't know what function to choose a priori. If we know it, then yes, you could do it. Yeah.
So when you're talking about the higher order interaction,
yeah.
Is it like you have a species, you can select if it is a predator and it has 4 to 5 prey, you can choose between any of them. So if you consider only 2 of them, then that will be different when you put all of them together. You can choose any of them. So
yeah, no, here really we're not talking about choice so much, right? What we mean by higher order interaction is the following. Say there's a species I and a species J, and there's some interaction between them, right? Let's say just say A inhibits J, I inhibits J, right? Usually in our matrix there'll be an AIJ here, right? Now what usually happens as a result of the higher order interaction is there can be a species K, and its presence can itself modify this interaction. That's what we mean by higher order interaction. And typically the way you write it down mathematically is that you have this equation. That's with no higher order interactions. With higher order interactions, you will have something like Bijk, Xj, Xk, and this is a double sum over J and K. That's what a higher order interaction would look like. You can imagine 4th order, 5th order, and so on and so forth.
And for other thing, the evolution.
Yeah.
So in evolution, you can also have it will give rise to new species, right?
Yes, exactly.
The whole size of AJ will increase.
Exactly. The size itself is dynamic. The degrees of freedom of the whole system are dynamic.
So total S will live.
Total S can keep changing. Yeah.
So when you're talking about this soil, 1 gram of soil having thousands of species.
Yes.
So we do say that they are coexisting, but we don't know about the species that have already gone extinct in them.
Yeah.
So
we know a little bit because you can pull out what is called necromass. You can pull out dead cells.
Oh.
Yeah.
So yeah, if we don't know that, then it will automatically indicate like this is another stable state.
Yes.
Where some species has gone extinct and some other survive in
Correct. Correct. Yes.
What is the Lyapunov stability? There is a brief description of this in the website which you have referred to.
Yes. Okay. So Lyapunov stability just has to do with this idea of global stability that we were talking about. So typically, in some of these systems that we were talking about, you can take you can go to multiple stable states, right? Based on the initial conditions that you can choose, you can either go to one or the other. We talked about an example last time of a bistability, right? So in some cases, especially one of the cases is when you have your interaction matrices be symmetric, then you can show that there is a function f such that on the dynamics df over dt either always increases or always decreases, right? And what this means is that this, because of this reason, system always proceeds in one direction towards one state. So there's one globally stable state, and that also sometimes is called Lyapunov stability.
That means the globally stable state and the Lyapunov state are synonymous.
Yeah, I mean, Lyapunov stability is one way of getting global stability.
It's a technique.
Sorry?
It's a technique.
It's a technique. Yes. I mean, Lyapunov stability is a statement about the system, that the system is Lyapunov stable. The system is not Lyapunov stable, but finding a Lyapunov function is a technique. You know, I didn't say anything about how you find this f or whether it exists or not. Proving that it exists or doesn't exist is a technique.
He was mentioning about the one predator, but like multiple prey.
Yes. Yeah.
Right?
Yeah.
So is that just like the predator like interacting differently with each of them? So
yeah, correct. The lion likes to eat the rabbits more than the hamsters or something like that. Yeah.
And that would depend on their availability and.
Yeah, or some predation rates or some energy that they get from them, some combination of all of these things, right?
Professor, I have a question.
Yeah, maybe we'll take the question on Zoom first.
Okay. So I had a question about how we're defining the interaction terms. So, for example, say when you have three species, like say you have ants, aphids, and plants. The ants may be like rearing these aphids, and these aphids say they have a negative effect on the plants. So the ants have an indirect positive effect on the plants through the aphids. So mathematically, when we're taking the pair of ants and plants, we sort of have to factor in the aphids into their interaction term, right?
Correct.
So how would we do that?
Yeah, exactly in this higher order interaction way that we just talked about.
Oh, using A, B, and
yeah.
Okay. And say you had like over here we're using linear terms for mathematical simplicity. But why do we assume that that's a good enough approximation for like real systems?
Yeah, good. The reason for that is that really what you're imagining often in these Lotka-Volterra models is what we often in physics call linear response theory, which is that you have some dynamics, some species Ni, right? That's Ni times some Gi of n. And let's say we don't know what this Gi of n is, right? What you can do is you can always say around some fixed point, I can ask what the dynamics should look like. And when you expand this Gi of n, which is where Gi is some arbitrary function, then in that case, you'll see that it like the highest order term that you should care about is a linear term. So the strongest contribution around some fixed point is going to look, so around any fixed point, actually any ecological dynamics should look like a Lotka-Volterra model. Did that answer your question? That's how folks justify it. And then of course you can justify it by trying to fit the data to experiments, right? Which also people have done.
Right. Okay. Thanks.
Yeah.
The alley effect is kind of a higher order interaction.
The alley effect is actually it's not higher order, it's actually lower order. Like a higher order interaction means that the presence of other species affects what's happening between two species. Alley effect is the presence of what's happening within the same species is affecting the growth rate, right? So it's actually a lower order interaction.
And suppose you're given a random nonlinear differential equation or something.
Yeah.
How do you know whether chaos will happen or not?
It's generally very hard to say. Yeah. You can numerically say it. If you happen to guess the right parameter region, you can measure something called the Lyapunov exponent, which is to ask how quickly, whether or not and how quickly two nearby trajectories diverge. Analytically, it's very hard to say anything general. Okay, if there are no more questions, then thank you so much. Thank you for taking this module.
Sir, I have a question here.
Oh yeah, go ahead.
Okay, so you were mentioning about this hyperbola wala, this scale, we move from the stable to unstable region.
Yeah, sorry, I couldn't hear you. You said something about the hyperbola, right?
Yeah, I was talking about this when you increase the number of species and try to plot it against the connectedness of the system. So
Yes.
you have this unstable and stable wala region.
Yes.
So let's say we have to do this experimentally. So how do I know this tipping point? How many number of the
How do you know the
particular?
what?
How do I know this tipping point where the system
Yeah, you
converts
don't,
from
yeah,
stable to
you don't know
unstable?
the phase boundary. You don't know the phase boundary. You try to just explore the parameter space and ask if there's one region in which one thing happens, the other region where the other thing happens.
But
You don't need to know the boundary.
it might happen like, let's say somehow I know that I am at the phase boundary. So just adding one number of the particular another species will just lead to tipping point, or do I need to like add multiple number of the same species, but different species and multiple of them? Let's say
I'm
need to
sorry, I'm actually having some trouble hearing you well enough. So so maybe if you don't mind, could you send me this question by email? My email should be available.
yeah, I will then mail you.
I'm sorry, I'm not able to hear the question properly, so I'm not able to answer it.
Oh, okay, not a problem, sir.
Just send me an email and I'll answer it, yeah?
Sure.
Okay, sorry, thank you.